Welcome everyone. Today we are going to extend our knowledge of 2D vectors into 3D space. And to do this, we need to add an axis to our typical XY axis. Now we have the XYZ axis. And a really good resource for visualizing things in 3D is actually the Geogebra 3D calculator. So I'll show you what that looks like here. Can actually grab it and rotate it around like so, and just gives a really great visual for a lot of the things that we're going to be talking about moving forward. So our classic XY plane that we normally have in 2D space is kind of going to be like rotated and put on the bottom, and now this is going to be our XY plane here. We're going to use the right hand system, which is basically how we're going to orient our axes. There's lots of different ways that we can do this, but if you do a thumbs up, your thumb is pointing upward, and that's the positive Z axis. Your arm is kind of like your positive Y axis, and then your fingers will curl towards the positive X axis. Okay, so to plot points, we're basically going to have them as X, Y, Z coordinates. And so let's take a look at the point 2, -3, 7. We'll move out 2 units on the X axis. We'll move left 2 units on the negative Y axis, or sorry, left 3 units, and then up 7 units on the positive Z axis, leading us to a point out here. So I'll show you what that looks like in Geogebra. 2, 3, -7. To graph a point on Geogebra, simply type any letter, equals, and then open up your coordinate system. So 2, -3, 7, and then just click off of it, and it should graph your point, which I'm not seeing here. There we go. It's just a little bit off my screen there. We can zoom out a little bit. If you're zoomed in too far, you won't be able to see the point, which is, I believe, why I wasn't able to see that point previously. So now, here's the orientation. The X is representing, is the red here. The Y axis is the green, and the Z axis is the blue. So we can kind of see this point out in 3D space, where Z is 7, Y is your -3, and X is moved 2 units forward. Okay, so let's plot some points. Let's try 2, 6, -1. So we're going to go out 2 on the x-axis, over 6, keep it parallel to the y-axis here. Not a great line, but get the idea. And then we're going to go up 1 unit, and there's our point. So in order to see this a little bit better, if you just kind of complete the rectangle, it at least allows you to kind of see a little bit better where that point actually is in 3D space. All right, so you can kind of see that our point is like on the outer edge of this rectangle here. And we can take a look at it in Geogebra as well. So let's flip over here. 2, 6, 1. There it is. You can see it in 3 space. Up in this upper right quadrant here. Great, let's try 0, 0, 6. So 0, 0, 6 is actually an intercept. This is 0 for X, 0 for Y, and up 6 units on the Z axis. So it literally just intersects that Z axis at 6. And then 2, 3, 0, so go out 2 on the positive X axis. We're gonna go right 3. And we're not going up or down at all. So this is actually flat with the XY plane. And I want to show you this one on Geogebra. 2, 3, 0. Here we go. You can actually see that it's like literally in that plane right there because it hasn't gone up or down on the Z axis. Okay, let's take a look at -1, -3, 4. So -1 means we're going back on the X axis, and then -3. And then up 4. So we would expect our point to be kind of in this back left quadrant here. You can probably see it a little bit better on Geogebra. So I've graphed it here for us. You can kind of see it in this back quadrant as we rotate around here. You can also just let this kind of spin around so you can see it. There you have it. Okay, let's move on to vectors. So we can draw vectors in 3 space as well. So our vectors are going to be starting at the origin, which in 3 space is 0, 0, 0. And they're going to be traveling out to some point where the tip will be at some x, y, z coordinate. We also have unit vectors in 3 space, similar to our 2 space vectors. So our 2 space vectors used to be I and j as 1, 0, and 0, 1 respectively. Now we're adding on this z component here. So for I and j, the z component will remain 0. But now we also have another unit vector k, which is the unit vector in the direction of the z axis. So x and y are 0 for this, and z is equal to 1. And any vector can actually be split up into a sum of scalar multiples of the unit vectors I, j, and k. So we can kind of see here, if I split up vector a, b, c into a sum of each of its components, we can use these as the scalar multiples of the unit vectors I, j, and k, just to simplify this addition. And also we can extend our magnitude formula into 3 space. So typically in 2 space, we basically just had this without the z component. So x component squared plus y component squared, and then take the square root of the whole thing. In 3 space, we'll add on the square of the z component as well, and that will give us the magnitude of a 3D vector. So let's take a look at an example of those few things that we just went over. We're going to sketch the position vector for vector u, write it in terms of its unit vectors, and also find its magnitude. So in order to draw the position vector, we want to start at 0, 0. That's going to be the tail of our vector. And then we're going to sketch out to 3, negative 1, and 2. And that will be out here. So your vector is going to kind of look like this. And if you kind of complete the rectangle that this is inside of, you might be able to see it a little bit better. So I'm going to complete that here. Okay, so this gives us a nice visual of kind of the 3D version of what this vector should look like inside the rectangle. And we can see that this is actually made up of multiples of the unit vectors shown with the pink directions here. So this is I, j, and k. So that leads us to our next part here, where we simplify vector u into its components. Sorry, I put magnitude already. Jumping the gun. So this is going to be 3 times vector I. Vector I, sometimes you write it as a vector symbol. I like to write it with the hat symbol to indicate that it's a unit vector. Either one is acceptable. Okay, minus j hat plus 2 k hat. And I'll show you this vector on GeoGebra as well. So we're going to start with a point at the origin, and then I want to also graph a point out to my vector. So my vector here, just make sure I get it right, 3, negative 1, 2. And now that I have those 2 points, I can create a vector in GeoGebra really easy, just by writing a vector equals, and then you just put O, comma, P, the names of your 2 points, so tail and tip of your vector. And something's going on here, let me just look. Should be, actually, I think I put an equal sign there, so should just be O, comma, P, no equal sign. And then when you click off of it, it will kind of turn it into a vector format there for you. So we can eliminate those first 2 points that we created. We can actually see the vector in that left front quadrant there. So there it is. All right, so going to the magnitude of the vector, we're going to find the magnitude by taking the squares of each of the components and adding them, and then we'll take the square root of that value. So we're getting 9 plus 1 plus 4, which will give us root 14. Wherever possible, we're going to leave our magnitudes as exact values and as simplified radicals. So a couple formulas that we can extend from 2 space into 3 space would be our vector addition and subtraction. So you can see that these are the same as they are in 2 space, except now we just have the z components added on there. So add the components if you're doing a sum, subtract the components if you're doing a subtraction or a difference. You can find the vector between 2 points by doing tip components minus tail components. Keep the y's, x's, y's, and z separate in their own little coordinates separated by commas. And then we do have a magnitude formula above, but this is basically when the vector is given to us complete. So I would have to already know vector u in order to use this particular formula. This gives me a little extension of that. It allows me to find the vector between 2 points. So x components, the tip components minus the tail components, squared, plus squared and added, and then take the square root of the whole thing. So basically what it's doing is it's combining this formula with the one above. And then the dot product as well is very similar. Multiply the x components, add the multiple of the y components, and now this time we're going to add the multiple of the z components. So in order to find the magnitude of AB, I can use the formula here, but I'm noticing for part B, we also want to find a unit vector in the direction of AB. So I might just start here by finding the vector between the 2 points, and then we'll take the magnitude. All right, so AB, vector AB, I want to do tip components minus tail components. So here the tip of the vector is B and the tail is A. So I'm going to do each individual coordinate, tips minus tails, and that gives me the vector 4, 1, negative 3. Now in order to find the magnitude of this guy, we are simply going to take our components here and add the squares of them and then square root. So I'm getting 9 plus 16 plus 1, and that's going to give me root 26. Okay, you could have also applied this as well, and that would have done these two calculations kind of all together for you. But either way, you're going to have to calculate what vector AB is. So find a unit vector now in the same direction as AB. So just as a little reminder, in 2 space we talked about this, and it's no different in 3 space. So if I want a unit vector of AB, we use a little hat to represent unit vector, I'm essentially going to take 1 over the magnitude of AB, and I'm going to multiply that by vector AB. Essentially what I'm doing here is I'm taking vector AB and I'm dividing its magnitude out, giving the resulting magnitude as 1. So we found the magnitude above as root 26, and we know the vector is 4, 1, negative 3. And then we're simply just going to distribute this 1 over the magnitude into the vector itself. So you should get 4 over root 26, 1 over root 26, and 3 over root 26. Let's take a look at what this unit vector actually looks like in GeoGebra. So the first thing that I've graphed here is the vector 4, 1, negative 3. You can see that graphed along the side here, and then I'm going to add on a point at the point with the scalar multiple in there. So here's the point, and then I'm just going to do a separate vector here where we do a vector out from the origin to point A, which is the point with our scalar multiple. So I'm going to get rid of that point on the graph here, and you can kind of see this tiny little vector. Let's zoom in a little bit so you can see that a bit better. You can see that little vector here, and if we remove vector u, what remains is the unit vector in the same direction as vector u. So you can kind of see here as we rotate kind of what that looks like in 3 space. Okay, let's take a look at a couple other things that we can do with those formulas that I introduced above. We can multiply in a scalar multiple. So pretty straightforward. You're just going to take your scalar multiple and distribute it into each of your coordinates from your vector. So you'll get negative 24, 12, negative 9. We can also add vectors together by adding simply the x, y, and z components. So if I'm adding u, v, and w, I want to take the sum of the x components, the sum of the y components, and the sum of the z components. So that's going to leave us with the vector 4, -3, and -2. Okay, let's take a look at finding a magnitude of a subtraction of two vectors. So first it might be helpful for us to find u minus v. So I'm going to do u components minus v components. Okay, so here you can see I've taken the difference of the x's, the difference of the y's, and the difference of the z's, starting with vector u, subtracting the component of vector v. So here you should get -6, 7, -8. And then if we want to find the magnitude of this, we're simply going to take each of those components and square root the sums of the squares of each component. So if you're following along with us with your calculator, you can enter this in, but I'm seeing we're getting 36 and 64, which is 100, and then 7 squared is 49, so 149. Okay, the square root of 149 can't be simplified any further, so we'll just leave it in that format. Okay, and lastly, we can do the dot product between two vectors by simply finding the products between like components. So we want to find how the x's are working together, how the y's are working together, and how the z components are working together. So this is what you should be calculating. So you're getting 16 minus 12 minus 15, and that's going to leave us with the scalar -7, or -11, sorry. All right, we can extend our knowledge of collinear vectors from 2 space into 3 space as well. What I showed you before with these two vectors, one being a unit vector, these are actually collinear vectors as well. They're parallel vectors that are simply scalar multiples of one another. So I know here, if I want to make these vectors collinear, I need the ratio between the x's to equal the ratio between the y's and the ratio between the z's. So I can see here that these are already equal in ratio. That should make sense. And in order to kind of fill this in, I know to make 2 over something equal to 1/2 or equal to 3 over 6, a must be equal to 4. Now, if you can't solve for this quite as easily, I would just basically eliminate one of these, solve for the a, and then plug it back into your equivalent ratios here just to make sure that it works properly. So we can see if we plug it back in, that 1/2 does indeed equal 2 over 4, and that is equal to 3 over 6. So we're good. We can also calculate the angle between two vectors. And we're going to do this by using the rearranged version of the geometric dot product formula. So let's take a look here. Sorry. All right, so cos of theta is going to equal the dot product of these two vectors. So let's enter in the dot product here over their magnitudes. Or I should say the product of their magnitudes. Okay, so on the top, I'm seeing that we have 0, 8, and -1. That makes 7. And here we've got root 17. And we've got 36 plus 4 plus 1. So that's going to give us 41. And if you'd like, before you do cos inverse, you can just take the multiple of those radicals and express it as a single radical, which will be 697. You don't have to. It might just be easier for you to enter into your calculator. So we're going to do the cos inverse of 7 over 697. And if you're following along with your calculator, I would encourage you to try it with us. Make sure you're in degree mode. And I was just in radian mode there for a second, so I had to switch to degree mode. We're going to round to 1 decimal place here. So this should give us about 76 74.6 degrees. All right, we're going to finish up with two more examples. Find a vector that is orthogonal to 3, 4, 5. Okay, so orthogonal is a word that essentially in 3 space means perpendicular. So if you see this word, we're just looking for perpendicular. And just as a reminder, the dot product of perpendicular vectors is actually 0. This means that they are perpendicular or orthogonal. So here's what I want to do. I want to find some vector, x, y, z, that when dotted with 3, 4, 5 equals 0. So I'm going to have 3 times x plus 4 times y. Guess I don't really need the brackets on that first one. Plus 5 times z. And I want it to equal 0 if they are in fact going to be orthogonal or perpendicular. So the cool thing is here is that I can actually choose any values arbitrarily for x and y, as long as I can solve for a third value for z that makes this true. So let's say, for instance, we choose maybe x as 2, maybe we choose y as 1, and then we solve for the z that makes this true. So we've got 6 plus 4, and then I'm going to move that to the other side. We'll get negative 10, which makes z negative 2. So a sample of a vector that could be orthogonal to 3, 4, 5 is the vector 2, 1, negative 2. And let's actually look at what this looks like on graphing software. All right, so here I've got both of the vectors graphed. And, oh, I think I accidentally graphed. Forgot the comma here. Here we go. There they are. So you can actually see, if we look at it kind of like from this angle right here, these are meeting at a right angle. There are infinite possibilities for an orthogonal vector to our vector here. If you just hold your pen out in front of you right now, imagine finding a perpendicular vector. It could go anywhere around the circumference of your pen and also anywhere along the length of your pen. So there's tons and tons and tons of different answers here. I strategically kind of chose my x and y so that I would get a whole value for z. I was thinking if I make x 2 and I make y 1, then those are going to give me 10. And I was thinking 10 is divisible by 5. So sometimes it won't be such a nice answer unless you choose those kind of like strategically. Another thing that you can do here is if I set y and x equal to 0 and just solve for, oh no, sorry, that's not gonna work. We're gonna say, sorry, I can't choose 2 equal to 0 because then I'm gonna have an issue with only having the 0 vector. But let's say I choose z equal to 0. If I make 3 and 4, two things with multiples that can add to 0, then I'm good to go. So basically, if I just flip them and switch one of the signs, this will work just as well. So you can see that this is 0 equals 0, so this works. So let's take a look. So 4, negative 3, 0. And if we plot this on Geogebra, I'm just going to change this point right here. So we said 4, negative 3, and 0, I believe. Yep. And we can see another vector that from some view is orthogonal. So if you want to use the little trick that we talked about in 2-space by swapping the vectors, you can still do that. Let's say you swap 2 of the coordinates, switch the sign of 1, and make the other one 0. That always works. So you could try it with a different one here. Let's say you swap 4 and 5 and make one of them 0. Okay, that will also produce another orthogonal vector. So the other one that we did was this one. You can also swap 3 and 5 if you want and make one of them negative. Those are really kind of quick ways to generate orthogonal vectors. So these are also orthogonal vectors. Lots of different answers. Okay, and then our last example for the day is finding the magnitude of a projection. So just to remind you, when we're working with Cartesian vectors, the magnitude of the projection of one vector onto another can be found by finding the dot product of the two vectors over the magnitude of the vector being projected on. And just as a reminder, these are absolute value bars because when we talk about the magnitude of a projection, we actually want that to be positive because we're talking about the particular length of a vector. So let's find the projection of u onto v. That means I'm going to find u dot v over the magnitude of the vector being projected on, and then we'll take the absolute value of that answer. So in order to find the dot product here, I'm just taking the x components and multiplying, the y components and multiplying, and the z components and multiplying. And then I want to divide this by the magnitude of vector v, which will be each component squared and added together, and then take the square root of that. All right, so on the top, I'm seeing that we're getting 15 minus 6 plus 0. So that gives us 9. And on the bottom, we're getting 25 plus 4, which gives us root 29. And remember, this is absolute value, so if it were negative, I would make it positive. But in this case, it's positive, so it will just remain positive. So we get 9 root 29. Thanks for tuning in today, guys. Have a great day.